All right, everyone, exam 3. So I don't know when you're watching this, but obviously it's this week. Next week we've got an abbreviated schedule and of course a final exam review. I'll also release that early. That's going to be 2 hours long and pretty comprehensive. And then the final is scheduled for Wednesday, the Wednesday of exam week, 1 to 3. Of course, that exam will be just like this third exam, just like the second and first. Same number of questions, same format, it's just comprehensive. Third exam starts with the hydrogen atom wave functions, and of course I'm reviewing that, and ends with kinetics. Heads up, kinetics is a big part of this exam, maybe slightly less than a third of the exam, but closer to a third than not. So you really needed to have watched the last 3 lectures. If not, then that's easily more than a letter grade that you'll drop. Last bit, I've said this a million times, but let me just point out in your studying, like if you're watching this Thursday night, the exam's tomorrow, that cost you a letter grade. You may not believe it, but I've been doing this 15 years, and so yes, it has. So just think about that. What you could have done is what you could be doing for all your classes starting now is if you're going to study, say 5 hours for every exam, if you're going to do them all at once, it's like too many people trying to go through a door at the same time. None of them come through. If you're going to spend that time, space it out, because then the characters can get through the door, right? And again, if you're still going to spend this time, it doesn't really matter when you do it. You can simply choose to make it effective by pacing things out, or you can choose to make it ineffective by trying to do it all at once. Each is the same amount of time. It just depends on how you pace yourself and schedule things and plan ahead, right? There's no extra effort. The only thing that changes is probably a letter grade, which that's the only effect, and that's an effect you probably would want. So think about that, because I would recommend that you would start studying for the final exam pretty much now. Start reviewing that older material. Start on that now, because in about 2 weeks you have your final, and I know you've got other finals, so you really need to have started studying for all these right now. Let's see, last bit. Yeah, I don't think I have anything else to say other than, normally when the class would meet for these exams, someone, because class is always at 2, I always start the final exam would be 1 o'clock, and at 2 o'clock someone walks in. That happens every year. What an idiot, right? And so of course online, I don't think, that's like the one thing I don't think will happen, so there's nothing to worry about there. Okay, I do remember one other thing. First exam, not so good. Second exam, people do way better. You did as well. The third exam tends to be in between, and that's because I think you've kind of let your guard down. I know you're all tired, and the nature of this material is that it's not so connected. There's lots of like modules. They're not quite connected to each other in a very sensible way, which is true. So there's a little bit more on the memorization side, a little bit. I try to make the test such that you could just maybe on raw mathematics be able to raw mathematics and horse sense do well on the exam, but of course to do that completely is not possible and kind of absurd. But that's the ideal I strive for when I write these things. So, and like all the other reviews, I have just finished writing the exam, so my review notes were modified with information that's on the exam. If you haven't figured that out yet, then you're not watching these videos or taking the exams. Okay, so, all right, with that, oh God, what do I want to do? Let's see, okay, we started with the hydrogen atom. I will not have really much of anything about the 3D rigid rotor spherical harmonics. That was more of an exam 2. It's kind of a little nebulous. Where does exam 2 and exam 3 begin? Because there's some overlapping material due to the fact that we were working on the 3D rigid rotor in exam 2, but those are part of the hydrogen atom. So it can be a little unclear where we started and where we stopped. So I'll try to make it as clear as possible during this lecture. So exam 3 does start with the hydrogen atom, and I'm going to try to remember to flash that Hamiltonian above my head. And how did we do everything with quantum? We have a Hamiltonian, an 18th century mathematical textbook gave us wave functions, right? So Hamiltonian to wave functions, and then we did things with those wave functions. We calculated energies, and then what other properties we could possibly calculate, like intro to spectroscopy, transition dipole operator, difference dipole operator. Those are the same thing, different words for the same thing, right? So we did everything we possibly could think of with those wave functions. So of course the wave functions look like this. The radial, so the radial wave functions are really the important ones. Those are like from the alpha, the primary Schrodinger equation. We had many Schrodinger equations for phi and theta. Those were the 3D rigid rotor. The radial part is where the energy is solved, so that's like the primary Schrodinger equation. And it has a normalization constant, who cares? There's this R to the L component. Remember, you actually don't see it in an S state, but that's because L is 0. And that has to do with the electron. If L is not 0, when I'm talking about a P or a D or an S state, that is there because you have to think about what happens as the electron gets closer to the nucleus and is twirling faster and faster. There's consequences to that, so that's where that comes from. Then we have some kind of connector that generally just introduces nodes as you go up in energy. As you go from n primary quantum number, n of 1 is of course for hydrogen and helium, n of 2 is the second row of the periodic table, carbon, nitrogen, all that, lithium, all that stuff. As you go up in energy, your S states need to pick up nodes, your P states need to pick up nodes as you find P and D states and S states and all that. So the connector does that. You know you need nodes to pick up kinetic energy, and then at long distances, you have to have something that looks like that. So this is for the first row. It's like R over 2A naught for the second, R over 3A naught for the third row. And that means that the wave functions get wider and wider and wider, which, hopefully is just kind of obvious, right? What do I want to say about this? Let's see. Let's plot some of the wave functions. Now, one thing I've done in the past, for those of you who have old exams, I have at times plotted wave functions and said identify them. I did not do that this year just because I didn't feel like it. Number 2, I've done it so many times. So, but still, you still want to recognize these things. So, of course, this is a 1s state. It's just an exponential decay. So that's a 1s. A 2s is similar, but there's our node. So you can see a node there. So that's a 2s state. And remember that these are finite, 0, 0. These are finite. That means it is not 0, finite, at the origin 0. And that's okay because the electron in S state is not rotating. Or I've said that a zillion times. I'll put that on the final. The wave function's round, but it's not rotating. And the only explanation I can have for that is P states and D states, which are rotating, have nodes, right? So a P state has a node, and nodes mean kinetic energy. If it's got rotational kinetic energy, then it has rotational kinetic energy, therefore you have to see a node. Nodes mean kinetic energy, right? It's just hard to visualize for angles. Oh, and anyway, so let's see, and don't forget that we can also plot R squared, which is like from a Jacobian, and we can also still do that for S states. And remember that that's actually why they don't hit the nucleus. So again, it's fine for them to be finite at the origin because they're not rotating. If they're not rotating, you don't have to worry about their energy, kinetic energy, going nuts as they get closer and closer, like a figure skater. But why don't they hit the nucleus is because they can't find it. So this is a radial distribution function. It represents better, this is a better representation because it expresses the effect of volume. So at low R you have no volume, at high R you have a large volume, so that compensates for the fact that you're less likely to find the electron there. You're less likely to find the electron at far distances from the nucleus, but there's also more volume for it to be in, and that kind of balances it out a little bit. Okay, and then for P states and D states, P states and D states actually look kind of similar, so it was always kind of difficult for me to ask questions because you could kind of mistake one for the other. So they're like a 2P and a 3D. Has a node, and I don't think I'm drawing that very well, but in terms of like their relative magnitudes, but it gives you the idea. Then of course these are 0 at R equals 0. Always label your axes. And that's because volume elements aside, you cannot allow the electron to get too close to the nucleus because it's rotating so fast that it doesn't have the potential energy to overcome the kinetic energy such that its energy is its energy, right? You had a homework on that. I'm not explaining that well, but you had a homework on that. So again, if the wave function didn't taper off to 0 at R equals 0, then the electron is going to start rotating so fast that you just can't conserve energy, and that's not okay. Now remember also the strangest thing about, one of the strangest things about hydrogen is that I plot the energies in the, you remember this, mathematical quadrants, 1, 2, 3, 4. You plot this in the fourth quadrant, so negative energies, and negative 13.6 eV is where the 1s state is, and you had to solve that on a homework. So here's the 1s, and the energy is of course a function of the primary quantum number, which we know to be the rho of the periodic table, 13.6 over n squared. And so the 1s energy is at 13.6, and 2s is higher. Of course, 2p is degenerate with the 2s, and then we've got a little bit closer. I'm not doing the spacing right, but I'm doing the best I can. Gets the point across. Then you can have P and D functions, and of course we go to the fourth row, then you can have F functions and whatnot. And it's negative because of the Coulomb operator, because in all of our previous models, you never had a negative potential energy, right? Potential energy, let's think of a harmonic oscillator, right? The potential energy is, at best 0 when you're at equilibrium. And if the thing compresses or expands, the potential energy rises. Then a lot of our other models were flat potentials, so there's no potential energy. So we never had a negative potential energy before, and it just makes the total energies negative, which is okay because everything is relative, right? Again, this is actually kind of makes my nose bleed sometimes because occasionally I professionally do like calculations on this stuff, and they're part of my papers, and I cannot express how many times I've had problems because the energies are negative, and I like forget that, or it does something weird. But remember, like if you're looking at transitions between states, remember that Reitz combination rule. That was the first lecture when we got into this part. You have the final end state minus the initial end state, so it would be minus 13.6 n 1 over n final squared minus 1 over n initial squared. And that transition would give you a positive energy. So, which makes sense. You have to, if you want to blow a hydrogen apart, you have to put energy into it. Oh God, let's see. Then what do we do? Then there was, keep track of time. Other things now, this, where am I at? Sorry. Actually, I don't think this made the test, but I should express this anyway, that when it came to the angle parts, I find it kind of fascinating that, as I said a couple times already, the 3D rigid rotor are the solutions to the angular wave functions. It's all separated, right? Radial, theta, phi. Theta and phi come from the 3D rigid rotor. And those are legit solutions to the hydrogen atom. However, when it came time to put these in freshman chemistry and high school chemistry textbooks, you have this whole problem of, remember, traveling wave versus standing wave. Remember that the 3D rigid rotor has e to the I phi in it. We don't want to have to explain that, because you'd have to, right? If you want to show those things, you have to explain what that is. So a clever solution is to simply take a L plus m plus or minus wave function L minus m theta phi, and then those e to the I phi's go away, right? Now again, you worked a pretty long homework problem on that, so you know about that. Linear combinations, plus minus, wave function plus another one, is itself a legitimate solution. Maybe I'll put that on the final. And that's why that works. And it also avoids the trap of having to explain something kind of complicated to a 16-year-old. But it is unnecessary. These crazy-looking wave functions by themselves are totally fine. It's one of the weirdest things about this stuff. But I did not think I put that on the test. I did not put that on the test. So don't hold me to that. I'm pretty sure I did. Okay, then we had, before we left the hydrogen atom, we went into some spectroscopy. I actually spent most of our spectroscopy on the hydrogen atom because you can actually solve on pen and paper or using that website. And again, you had several problems on a homework. Hopefully that was really straightforward. What's kind of funny is, right, this is an expectation value. So when you have expectation values, you're going to have integrals, and you're going to have an integral of a final state, which is different than an initial state. So that's where it's a little different. It's a little different is that normally for expectation values, it's just, like ground state complex conjugate of the ground state. But in this case, they have to be different because there has to be a transition from, let's just say everything's in the ground state. So you're going to go from a ground state to an excited state. So that's why this is a little odd. That's a ground state and then that's in higher excited state. So you never saw that behavior on any of the other expectation value stuff that we did in the middle part of this class. Whatever. The thing that's kind of annoying about it is that it gives it two names, right? It's a difference dipole. It's the transition moment. It's the difference dipole. Again, I hate how so many things have multiple names, and I catch myself using those different names, and so I have to tell you about them. I mean, I probably should no matter what, right? The other interesting thing to note is that the dipole operator, because we talked about just classical electrostatics, we reminded you of, why am I saying we? I reminded you of your second semester, right? Second semester physics. Remember first semester physics, F equals ma, and you're like, oh, this isn't so bad. Then you get into E and M in second semester. It's like way different. But whatever you had it, you got through it. And dipole is charge 1, charge 2 divided times the distance. And so if you see that behavior here, what's kind of interesting is, here, let me write, I try not to do this, but I sometimes write over what I'm doing. So sometimes, I guess in all the homeworks, these ended up being negative quantities, but it doesn't matter. Remember, what we're looking for, is it 0 or not? And is it 0 or not? And that gives us selection rules. So that's what we're really trying to get to, is selection rules. And maybe that's just so we can easily express this to freshmen. Now, delta n has to be plus or minus 1. If we're at the ground state, the initial n is 1, so you can only, you have to go plus 1, right? Because there is no minus 1. There's no n of 0, right? The ground state is n of 1, first row of the periodic table. So this is just from conservation of energy. And you get this L plus or minus 1 or 1 h bar, I guess. Technically, you know, I often forget that these have units of h bar. Everyone's so used to it, it's almost pretty universal to see it left out. Doesn't matter, you don't need to know that for the test. And that comes about because of something funky here, is that light is polarized. Now remember that I went off on a lot of detail on left and right circling polarized light. Remember that? I did that because that's really what light looks like. And you probably had, most of the times I've taught this class, people said they never heard of that before. And that's fundamentally what light looks like. It's actually rotating when it comes at you, right? Left or right. Right hand, left hand. Nuts, huh? So where does plane polarized light come from? Well, plane polarized light is from, here, let me draw an atom, right? Plane polarized light is actually left plus or minus right circularly polarized light. And that's how you make it plane polarized. So plane polarized light does exist, and you use polarizers to do that. You probably played around with those in high school. And you make them by adding or subtracting circularly polarized light. So that's how they work. Most spectrometers, most of the UV vis in PChem lab, that actually has plane polarized light. It's way easier to build the spectrometer with plane polarized light. So all those times you saw light drawn this way, because I mean, how would you remember how complicated it is to draw circularly polarized light? When you've seen plane polarized light since high school, that's actually not a lie. It was just, there's more to it, and generally people don't mention that. So, okay, so there's polarized light, and here's other polarized light. Hopefully I'm drawing that okay. And that means that you actually have an angle part. R is actually hiding angles in it. And the favorite example is that if you're going to have Z polarized, what you've got is R cos theta. So as soon as you have that, now you've got the transition moment now has an angle part. And again, you work the homework, right? So you can see that delta L has to be plus or minus 1. And again, we always assume that the thing is in the 1s state. Here we go. And so that means that with light, you cannot go to a 2s, because that's a delta L of 0. You have to go to a 2p. And if you have X polarized light, then you're going to have to go to a 2pz. And if you have different polarized light, you can go to px or py. Now, one of the neat things is, this isn't on your test, but I wanted you to tell you about this because it's kind of cool. Let's say that you shine light, X polarized, Z polarized light on a hydrogen atom, and so now it's in the 2pz state, just for the heck of it. Okay, now you've got a 3s state, 3p state, 3 of those, and then you got 3d states, and you have 5 of those, and you know what those states are because you had to work a homework problem on them. And you know what I was trying to do? I was trying to make one of those videos to show transition. Remember how I showed you a video of 1s to 2pz? Spent weeks on that, by the way. I was actually working on one for 2pz to 3dz squared. I was trying to do that, but it looked all funky, and I don't know why. It was like looking weird. Kind of looked right, but not really. And I realized that what I was seeing was a transition to both. The 2pz state, and I did that little simulation, I made my little video, it actually can transition to a 3D or a 3s. So it actually kind of transitions to both simultaneously, which is actually what it's supposed to do. And the video looked really weird, so I didn't show that because it's just kind of funky looking. Anyway, this is just another example of how that selection rule works, so that's why I'm just talking about that. Oh God, let's see. Now notice that when we did all this, let's see. Well, okay, so let me just do this, right? So you can have a spin-up wave function, or you could have a spin-down wave function. And you weren't taught really too much about spin up or spin down. Well, I mean, you've seen up down, right? When you talked about the Aufbau principle in high school, when you did this in freshman, you should have done a little bit of this in organic when you're talking about ligand field, D to D transitions and all that stuff. So, spin up, spin down, Aufbau principle, build up principle. For the hydrogen atom, you don't need to worry about it because spin up or spin down, it just doesn't matter. It just doesn't do anything because there's only one electron. When you have two electrons, then you need to keep track of it. And let's see, where am I at in my notes? So technically a hydrogen atom is a radical. But you don't have to worry about writing anti-symmetric this or that, alpha beta minus beta alpha. You don't have to do that for hydrogen atoms. So it just isn't important. So it never got brought up probably in any of your classes other than just to learn that rule about how to write out electron configurations. Let's see here. What do I want to talk about next? So at this point, I have to talk about the multi-electron deal. So tell you what, let me wipe out the board and we're going to look at the Hamiltonian and start talking about molecules, wave functions, and all the approximations made there. So 1 second. Multi-electron atoms or molecules, not terribly different, right? Because they both contain multiple electrons. And as soon as you have more than one electron, even if you're talking about just like an H- atom or an H2 molecule or DNA, you got more than one electron and now you got problems. So I'm flashing up the multi-electron Hamiltonian, and the problems you run into are those last two terms. You've got that 1 over R1 minus R2 deal. Electron-electron repulsion. Sometimes I put R2 minus R1, R1 minus R2, but it's the absolute value. I never keep it straight which one I do, but it doesn't matter. Okay, so either way, that next to last term is the electrons repelling other electrons. Of course they do. How could they not? And you have to leave that in there. The problem is that now the wave function cannot be solved with like an orbital for electron 1 times an orbital for electron 2. You cannot write, that's the separated way. But that Hamiltonian with this freaking term, remember how we separate Hamiltonians into miniature Schrödinger equations? It's impossible with this. It cannot be done. So we have no way of solving these things. And if you think about it, how could we? You'd have to have the coordinates of one electron would have to be functions of the coordinates of the other electron because they can't like run into each other, and also vice versa. How would you do that? I mean, I have no idea because the electron, electron 1 can be anywhere unless the other electron's there, but the other electron can be anywhere. So what do you do? And no one knows, all right? So what we do is we're going to write this anyway. The orbitals will still be like, so let's do H minus because, so 1s2 hydrogen atom is an H minus. Oh, why am I trying 2 levels? So let's do a singlet. And so what these orbitals are, these orbitals would just be 1s hydrogen states, but those are not the real solutions. Not just because you can't just multiply them together, all the things I just said. It's because the hydrogen atom is neutral. So it's much easier like, oh yeah, oh here's a hydrogen atom, and I know that 1s state. That 1s state is like e to the minus r. So I just have two of those wave functions when I add a second electron. The problem is that this idea of a wave function of a 1s wave function being e to the minus r only comes about from a solution with an atom with 1 electron. If you have 2 electrons, there's no reason to think that you're going to get the exact same thing. In fact, it certainly isn't the same thing. It should be close, but it's not going to be exactly the same thing. But we don't know what it is because, again, we can't solve it to begin with, right? So it really kind of, I know it's a lot to take in. I'm just saying we don't really know anything, so we make this approximation that it's close enough that the 1s state for one electron will serve for an H minus when I have two electrons. And then we do that going forward with more complicated things with other elements and with molecules. It's like hydrogen-like orbitals on all of them, even, because we just don't know what else to do. So, right, so again, separating these is wrong, but we're stuck. Now also note that then we have to worry about the Pauli principle. So like one thing I would do, I didn't do this on this, no, I did not do this on this test, but like here's a good what's wrong question. Let me half backtrack on what I just said, whether I did or didn't do this. Anyway, okay, so I would say which one's lower in energy, the singlet or the triplet state? And I would say, well, the triplet's lower in energy, right? No, what's wrong is you can't have a triplet state. You can't have two electrons in a 1s orbital and be triplet, right? Up is not up or down, that's not allowed. That's the Pauli principle, right? You can't have two electrons in the same state at the same time. And remember the way that we deal with that is for our singlet wave function for one, you have to make certain, I hate the complication of this part. You have to make certain that you can't distinguish the electrons. Excuse me, that's not really a big deal. But then you have to make certain that if you draw, spin up in the same orbital, that's not allowed, and you do that this way, right? You had a whole homework on this. If you were to do spin up, you'd have alpha 1, alpha 2, minus alpha 1, alpha 2, minus alpha 2, alpha 1, which is 0. So that's how that works. And I didn't go over this, but if you have 3 electrons, you can imagine like, alpha 1, beta 2, alpha 3, something like that, minus. Actually, that won't work. These get really, really complicated, such that if you switch any 2 electrons, you have to pick up a minus sign. Remember that the Pauli principle dictates that if you have this, if you interchange the labels on your electrons, you have to pick up a minus sign like that, and that's what this does. Now recall the reason that is that if you make a hydrogen minus with 2 electrons spin up in the 1s state, then the wave function is 0, right? So you're not allowed to do that. Okay, so there's that. So that's the singlet. Now you can still have triplet states, right? You just have to have a 1s, 2s, or 2p, doesn't matter. Okay, so that's triplet. Up, down, or up, down, plus down, up, which again, remember we talked about that, that's a weird one. And that one has the anti-symmetry, this part has the anti-symmetry in, sorry, I have to, it doesn't matter how I write it as long as I make sure I permute the labels. So the anti-symmetry to interchange is done in what's called the space part, and the spin part ends up being kind of easy, alpha beta plus beta alpha. And again, I explained that last one. I did my best to explain this last one, which is really freaking weird, but anyway. Okay, so there's your triplet, and oh god, what else was I going to say about this? So it turns out that the triplet usually, the triplet for an H2 minus is actually lower in energy than the triplet, than the singlet. And one of the reasons is that if you look at, this would be for an H, so I'm actually drawing an H2 molecule, sorry, I wasn't thinking there. The triplet, because of this anti-symmetry in space, causes the electrons to not get so close to each other, and that ends up being an energy lowering. Whereas for an H2 singlet, you would actually have the electrons kind of close to each other here, and so there's a lot of electron repulsion, and that raises the energy a little bit. So If it comes, oh, that bothers me, it has to be, I need to have it symmetric. When it comes to, there we go, now I can sleep. Now when it comes to more complicated atoms or molecules, it is generally true that the triplet is lower in energy than the singlet, but you can't take it for granted. The one thing that you should be getting from all of this hideous complication is exactly that, it's complicated. So when you start describing DNA or proteins, and these things are literally, you have to be put on a supercomputer, you can never write them out, they're millions of terms. There's no general rule that any, singlet's going to be lower than triplet or triplet lower than singlet. You can't presume that. That's why we have supercomputers. But for the hydrogen atom, you can still see the underlying mechanism, because that's the one thing that I can write out, and beyond that I can't. And recall that what happens is that the energy of an H2 minus or an H2 molecule is going to be the kinetic energy, which, sure, kinetic energy, that's, as much as that's the hard part of the Schrodinger equation, I think you know what kinetic energy is. And then you have the Coulomb, that's the electrons interacting with their nuclei, and electrons repelling each other, but then you get this plus minus exchange thing. It's plus for a singlet, minus for a triplet, and again, that's just from wave function, Hamiltonian wave function. The wave functions are anti-symmetric from the Pauli principle. It ends up being, remember when we did this, it's like 80 different terms, and one of them is this exchange. Well, let me write down the Coulomb first, because the Coulomb is really simple to understand. Here's the second electron interacting with the first electron. We know that a wave function squared represents where the electron is. So this is perfectly sensible. Electron 2 interacting with electron 1, they don't like each other, energy raises, sure, whatever. I mean, totally sensible. But the exchange, because of this Pauli thing, ends up being just ridiculous, where you have the electrons, like, that's electron 2 in 2's orbital, which makes sense. But that's electron 1 in 2's orbital. What's it doing there, right? I don't know. None of this makes sense. No one actually understands this beyond the fact that, I can solve all this for a hydrogen atom. There it is. And when we do spectroscopy and whatnot, yeah, it's there. Yeah, it's absolutely there. How it makes sense other than just this is what my derivation gives me, yeah, that's all I got, and that kind of sucks, but here we are. The other neat thing is that, remember I'm going to switch back to hydrogen H minus. That is magnetic, right? That's a triplet state, and that's magnetic, like magnets on a refrigerator magnet, not like NMR magnetism. That's for a nucleus. Nuclei are magnetic, some nuclei are magnetic, but that's a really weak interaction that you can't build refrigerator magnets based on that. Electrons are magnetic because of that spin, up, down. That's a very strong form of magnetism. So this H minus atom is very magnetic, but if it was singlet, which is higher in energy, then it would not be magnetic. The last bit I wanted to say before we get on to spectroscopy was, as much as we write space, and I have to show that Hamiltonian, and spin, alpha beta minus beta alpha, remember that is an approximation because the last term on that Hamiltonian is L dot S. Remember that spin orbit? That is because an electron whizzing around an atom creates a magnetic field. Anytime an electron accelerates, it's generating a magnetic field. But it is a magnet, so it interacts with its own magnetic field. Which is like, okay, it makes sense, right? It's just like there's like a lot of layers to this. Regardless, the L-type magnetism, and that's why there's an L in the operator, and it's S-type magnetism, which is just inherently, an electron is inherently its own magnet. That's why you see L dot S in that. That's an interaction. And it's why singlet and triplets can convert between each other. It's the difference between fluorescence and phosphorescence, which you should have had in PChem lab. But it also means that you can't write wave functions this way. I can't technically do, psi 1, psi 2, alpha 1, beta 2 minus beta 1, alpha 2. You can't technically write them separately. But again, we don't have a choice because we don't even know what the proper wave functions are for spin. We just call them alpha and beta. We don't really know what spin is, so we just use these impronounceable symbols to represent spin wave functions, but we don't even have functions for them. They're not e to the theta or any of that jazz. They're just alpha, beta. So that's another approximation that we have no solution for. Okay. Last bit was to talk about Hamiltonian. So I did have an extra hour where I talked about, and you have that on your current homework, how when it comes to molecules, I didn't spend a lot of time on this, and what I'm showing you is a bit of an approximation. But if we're going to do, let's say, let's look at p states for let's do oxygen. So there's an O atom interacting with the p states of another O atom. And if you want to talk about the orbitals of an O2, the way you do that is you use a completely different form of quantum mechanics. You use the matrix form of quantum mechanics, which, to be honest, is actually kind of easier. You just got to remember that all these approximations I've been yammering about are alive and well for these. And so what you do is to describe the bonding, you make the Hamiltonian matrix. And the Hamiltonian matrix looks like this. There's atom 1 and atom 2. So you have a top, and you have them on the sides, and the Hamiltonian matrix represents their interaction. So an atom's orbital, atom 1 p orbital is just going to be EP. Let's do X, EP Y, EP Z. That's for atom 1. Atom 2 has the exact same, if I'm talking about the same atom, and I'm talking about its p orbitals, then those are the exact same thing. Okay, and what this represents is, this part is just the atom's energies by themselves. Okay, but when they start to interact, let's see, an atom does not interact with its own py or pz orbital. How could it? That doesn't make sense. They're just hanging out from each other. However, atom 1 can interact with atom 2. So the px of atom 1 can interact with the px of atom 2 with some amount of energy, and maybe it doesn't interact with y or z. And the y of atom 1 can interact with the y of atom 2, and the z of atom 1 can interact with the z of atom 2. And then vice versa. So anyway, I'm not going to build this up because, to be blunt, I'm actually doing one of your homework problems. I don't know if you noticed that. But, well, here, I can't resist. I'll do this one. Anyway, so there you go. And then 0, 0, 0, 0, 0. Oh God, this is just a mess, isn't it? Sorry, it's hideous, but anyway, you get the point. Okay, and then what you do is this matrix, then you plug that into a computer, which again you did on your homework, and it gives out the eigenvalues. And the eigenvalues can be like EPZ minus the energy in the X, and then it turns out that the energy in Y and energy in Z are the same. So it predicts one of these and two of these, and then it says, oh, another eigenvalue is the energy of the Z orbital plus the energy of the X, and then there's two others that are energy of the Z, just the P orbital, just P orbital in general, right? Doesn't have to be Px, Py, Pz. Those are degenerate. And then there can be sum of the y and z. Now it turns out the interaction of an x, now here's an x, those interactions are much stronger. And so if you look at these eigenvalues and then plot them, you end up with something like this, right? So this is a px orbital. This is py, pz, pz. Now oxygen has 4 p electrons. The other oxygen also has 4 p electrons, so I have to account for 8. 1, 2, 3, 4, 5, 6, 7, 8. So bonding, 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 antibonding, antibonding. Regardless, so that's how we generate molecular orbitals, is from these matrices of atoms interacting with other atoms. The computer tells us eigenvalues. The eigenvalues I can then plot in some orbital diagram, and then I add my electrons. And then I can know something like oxygen is a triplet. That's why oxygen is magnetic. So there you go. This did make it to the test in one of the harder questions, so I hope you note that. If you don't mind, I'm going to go a little over. Let me wipe out the board. After all this hydrogen atom, this and that, and our quantum started tapering off, especially as we did more and more approximations, then we had the part where we kind of start going into a lot of minutia. I hope it was interesting, right? As college graduates, I hope you'd understand a little bit about the electromagnetic spectrum. Radio waves, the reason that radio waves are useful is because atoms and molecules don't actually absorb those low energy radiations. There's not a dynamic that allows that energy to be absorbed. There's no rotation, vibration, or electronic transition. Nothing has electronic transitions that absorb at those radio wavelengths. That's why they go through buildings and walls and sometimes kind of a mountain. It's how they communicate with the submarines, right? Very low frequency radio waves. And cool, right? Now we talked about how you generate radio and microwave. You have to get electrons oscillating up and down. You can use a giant tower, or you can make the electron spin around in a circle. And it's not trivial to make light at other wavelengths than visible. Now visible, of course, we just use a filament. And we basically do that with the IR2, but that fails for all the reasons we talked about in the Planck distribution. That does not work for radio, microwave, or X-rays, or even UV for that matter. So for these guys, we have to oscillate. I have to oscillate electrons up and down. Microwave, you run into a bit of a problem. You know, we're starting to get to the point where between micro and radio is where our cell phones work, because you can't get too close into the microwave because things that can rotate, like HCl, things with permanent dipole moments, molecules with permanent dipole moments can rotate, and the rotation is a dynamic that absorbs microwave radiation. So microwave radiation does not go through walls, does not go through things like radio does. Microwave is stopped. It's stopped by molecules that can rotate. Atoms, of course, can't rotate. So there you go. Of course, that's how microwaves work. They actually are set to the frequency of water rotation, so they heat water up, because all your food contains water. That's why that works the way it does. Oh God, then what? Okay, then we have glow bars. Infrared vibrations absorb that, so again, you can't really communicate via infrared because it won't penetrate anything really. Except that there is this region it's called the near IR, between visible and infrared. There actually is this weird dead zone where actually there are vibrations end and electronic transitions begin. There's actually this small dead zone, and that's where your night vision goggles work. So you kind of can see through the walls a little bit, but not too well. Okay, visible is visible. This is of course where valence electrons are now transitioning from ground states to higher states. So again, you start absorbing light again. And X-ray, so this is for valence. And then for X-ray, of course, are electron transitions. But those are core transitions. And remember, that means that a heavy element like gold, which has F electrons, right? That would be like its one S electron absorbing light. Whereas the visible, it would be those frontier F electrons, 4F or 5F electrons. Electrons on the very surface, basically. Those are absorbing light. But if you go real high energy, you can pop electrons out of the very core, out, the 1s state, which has all these other electrons on top of it. But if you hit it with the right energy, real high energy, then they can pop out. Now remember, when it comes to UV, we use plasmas to make UV light. X-rays, we have to use synchrotrons or some other crazy things. And that's all based on, remember that Bremsstrahlung, I'm not even going to write it down, it's German for breaking radiation, Bremsstrahlung. And the idea is that electrons, accelerating, and to bend the path of an electron is technically a form of acceleration. We talked about how the field lines of the electron get all wavy, and wavy field lines are light. So a synchrotron, like at Argonne National Lab, causes electrons to bend, and that's how it shoots out X-rays. And you even did a problem on this that, they spent $2 billion on that thing, yet that problem that you did on how much energy comes out is actually small. But, I mean, it's like you spent $2 billion and you're getting milliwatts out. Why did I buy this? Well, because it's the only thing we got. And the other reason is that X-rays, other than medical imaging, you have to do this with material science. There's no good way to look at like your semiconductors and your solar cells or your CPUs. The only way to meaningfully explore what's going on with them is to use X-rays. That's why we built that facility and several others just like it, because we are always studying our semiconductors for solar cells or semiconductors for computers. The only way we understand them and make them better is by X-ray spectroscopy. So that's why we did that. Sorry everyone, we had more people traversing the classroom again, so there was a bit of a break. Okay, so we just talked about different sources of light and how we make that light. Last bit is on spectroscopy of molecules and how the dipole operator gets a little bit more complicated. So remember that when we did hydrogen atom, there was just, where's the electron? It's just proton-electron. So the difference dipole operator was just, where's the electron? However, when you get to molecules, you have nuclei, multiple nuclei, and multiple electrons, and they're all creating dipoles, simultaneously. That means that you have to start thinking about, what if the nuclei are rotating? Well, those are rotating dipoles, right? Now, atoms don't do that, but molecules do. So what could happen is you could have electronic transitions, vibrational transitions, and rotational transitions all happening at the same time. The way that manifests itself is in two ways. In PChem Lab, you know that when you're doing vibrational spectroscopy, you get these other features, these finger-like features, which is you're looking at vibration, but you're also looking at rotation at the same time. And that's because, now remember, you're also in the gas phase. I think you're doing acetylene this semester, I'm not too sure, but I think you're doing acetylene. So you're looking at the molecule vibrating and rotating at the same time, because the difference, the dipole operator contains information about the dipoles that form from electrons and nuclei and the protons at the same time. So that gets complicated. And remember, there was a bit of a lecture on that, and I know that was kind of a tough one. When it comes to visible at much higher energies, there's my favorite molecule, pyrene. I have a paper on pyrene, so that's why I like it. It's in the UV region of the electromagnetic spectrum. That's like 300 nanometers, something like that. So that's in the UV. And you get these finger-length projections because you're looking at an electronic transition plus a vibrational transition. And you can also see it in the fluorescence too, right? Now you had that in PChem lab, your fluorescence lab, where the fluorescence and absorption spectrum basically kind of look the same. And the reason that's happening, people like to draw this. Now in your PChem lab, you have a little energy diagram for vibration and rotation, and I think I tried to draw that in class too, and it's hideous. But for electronic and vibrational people like to draw this one because it's a lot more understandable, which is that you've got your ground state wave function and you've got excited state wave functions. Both the Morse potential is the electronic energy here and here, but then these vibrational wave functions are vibrational energies, right? Vibrational wave functions are vibrational. These bigger curves are electronic wave functions. I can't draw those wave functions, right? Those are like P and Ds and blah, blah, blah. Okay, so then what happens is that you have some probability of going to the first vibrational state or the second vibrational state, and that ends up being what's happening in these different finger-like projections anyway. So that's the Frank-Condon effect. So that's like a really big deal in PChem, and people study this quite a bit. Okay. Again, I know I'm going to go maybe 10 minutes over. You know, send your complaints to the front office. But I hope you like the fact that, you know, I'm going to cover everything on the exam. So I hope that makes up for it. Last bit is kinetics. I'm going to be kind of brief. We're almost done. But kinetics is on the exam. All right. In years past, I normally haven't gotten to it, but this year I did. So it's on the exam. I put it on there because I consider this really easy, and you just had it. Now, if you didn't watch those lectures, you're going to drop really 2 letter grades. But you're not watching lectures. What do you think is going to happen? So watch those last 3 lectures on kinetics. These are going to be really easy questions. So what I've done is, like with everything, I just make something up, right? I'm sure that there's plenty of reactions that work this way. And it's important to know, the first question is this the stoichiometry, or is it the mechanism, right? If this is the stoichiometry, I'm just telling you that A and 2 B's go make a C, but I'm not telling you how. It could be true that this is actually the mechanism. Now, that would mean that an A molecule simultaneously finds 2 B's, and their atoms are arranged to form a C directly. There's no intermediates, and if there were intermediates, I'd have to write them, because if this is an expression of the mechanism, I have to put down the intermediates. So let's say that this is the mechanism. So in a typical way, I give a big hint, is I would have a rate written above the arrow, and so that's a big hint. And someone would have to tell you this. You don't know off the top of your head. And you remember that example of hydrogen reacting with bromine. It looks like a very straightforward second-order reaction, but the rate expression was ridiculous, and that was because what you were seeing is the stoichiometry products reactants, not the mechanism. The mechanism was way more complicated. Okay, now for this example, we're going to say that this is the mechanism, because if I don't have the mechanism, I can't do anything. I'm stuck. I have to know the mechanism to start writing down things like, what's the rate? Now, the rate is defined as the rate of concentration change, and I always like to do reactants because I'm always in control of the reactants. However, this is a negative quantity, and people don't like to put negative quantities. So we put a minus sign in front of that so that rates are always positive. And this would be basically the same for B, but it reacts a little too quickly because every A eats up 2 B's at the same time. And of course for products, when it comes to enzyme kinetics, which is what we're doing on Monday, people focus on the product, but it's kind of funny that generally most people try to solve the rate expressions with reactants. Because again, you're always in control of reactants, but once you mix them together, you're out of control. It's just going to do what it's going to do. So it kind of makes sense. Okay, this is the rate. Now this part's important. The words. The next thing is the rate expression, or the rate law. So I usually say rate expression. Okay, the rate expression is this deal. That's when you're saying the rate of change of A, I'm not going to put the minus sign here, I'm going to put it over here. So, okay, sorry, somebody knocked on the door. Okay, so the rate expression is this deal, and it's going to be negative for any sinks. Anything that makes A go away, so minus K1. Okay, what makes it go away? Well, it makes itself go away, so it's proportional to itself. And then the way it works is that b to the second power. And that's just because there's two b's for every a. That's just how it works. We talked a little bit about philosophically why. It's because I am responsible for my own dynamic, and therefore if there's more of me, someone is going to do something sooner than anyone else. So therefore, the more actors present responsible for a dynamic, the sooner the dynamic is observed. I know that's a mouthful, but it kind of makes sense, right? Okay, that is the rate expression, and now you need to integrate it. So then you're gonna write down the integrated rate expression. So rate expression, and then you integrate it. Now in class, we only did two examples, like on pen and blackboard. A goes to B, which was just an exponential decay, and 2A goes to B, which is a second order, and we could solve that. Okay, whatever. Anything else you do is a bit more complicated. Right now, you're doing that on a homework. What are you doing? A goes to B in equilibrium with C. Now that's relatively simple in my mind, yet it's complicated enough that when you set this up, and we have to work with the computer, because I want you, why do we have these things if you don't use them? But you have to learn to use them, right? So you had to learn to change these rate expressions into something that the computer understands, and then you have to understand its output and translate it back to kinetics. That's a reasonable thing for you to be able to do as a college graduate. Okay, in this case, I just want to point out, I'm not going to go any further than this, but I do want to point out that you can't work with this as is. I'm sorry, everyone, another interruption. We're almost done. Okay, so I want to point out, if you bring dt over and integrate both sides, you need to make sure that you can't treat concentration of B as a constant. It's not constant. It's going away, right? A is decreasing with time. Well, so is B. So if you're going to integrate this, you need to be able to distinguish. B has A dependence, right? Because every two molecules of B react with A. So they're tied together. So if you're going to understand the dynamics of A, the dynamics of B have the dynamics of A hidden inside of it. And you need to know that, or you can't integrate it correctly. So again, you can't treat this as a constant because it's not constant. Okay, now there's sometimes a trick, like on the homework you have a trick. There's actually a trick on this one. Now again, we have to show where is the A dependence, because we're integrating A, right? So it turns out that the concentration of B can be thought of its initial concentration minus, let's see, how about the initial concentration of A minus its future concentration. Now let's see here. At the beginning, the concentration of A would be A naught, so this is 0. So the initial concentration of B is the initial concentration of B. Hey, that works. Now later on, if A is gone, then you're going to have A naught, how much B is gone? Well, A naught actually times 2, right? 2 times A naught. So again, in the future, when all the A is gone, then the amount of B is going to be the initial amount minus 2 of the A's, right? Because every 2 molecules of B react with A. Okay, now once you insert this in here, then you go to a website, and you're doing that on your homework, and blah, blah, blah. It's a lot of fun. Yeah, and that's really all I have. That should be enough to answer it, to do the problems on the test, more than enough. But it is on there. Okay. Sorry this went a little long. Good luck. Not much after that. Again, I will be doing this again for the final. It'll be 2 hours long. I will release it early, so I'll film it this weekend. And we have 3 more hours together. I'll see you then.